All right, so I'll be talking about data analysis with vector functional programming. The agenda is very simple. We'll start with a very brief history of vector programming just to get a bit of context. Then we'll dive headfirst into Q, get a taste of what that looks like, and we'll end with an end-to-end example of a data analysis task in Q. All right, so perhaps unsurprisingly, vector languages use vectors as the primary data structure and vector operations rather than typically using scalars and scalar operations. So this isn't a new idea. The first language in this space was APL, which had its first implementation in 1965. So OK, maybe this is a new idea compared to traditional functional programming, if you consider the lambda calculus in the 1930s. And that's really just starting to have a major impact now. So hopefully vector programming doesn't have to wait the 80 or so years that functional programming had to wait. But we'll see. So it all started with Ken Iverson, who noticed some inadequacies in conventional mathematical notation and algorithmic notation in communicating algorithms to his undergraduate students at the time. So he reflected on notation as a tool of thought for a while, creating this notation that was just called Iverson's notation. And he's written a number of papers on this. One of his papers is just titled Notation as a Tool of Thought. This turns out to be his Turing Award paper, so if you're looking for some reading, I highly recommend this paper. But it's interesting to note that this notation was first created to communicate to humans before it was ever used to communicate to computers. This later became APL when Iverson started working at IBM with a few other people like Aidan Volkoff. This has had a number of influences on languages that you've probably heard of, things like Mathematica, MATLAB, R, more recently Julia. And it has a number of direct descendants that are still being developed and in use today. So there's a few dialects of APL that are still being developed, Iverson's later language J. And then Arthur Whitney has created a few languages like A+, K, and later Q, which we'll look at today. So that's enough history. That's the history out of the way. Let's dive into some Q. So we'll start off with function application. That's a good place to start with a functional language. So there's two sorts of these named functions. There's monadic functions and there's dyadic functions. Monadic functions just have a single argument. This has nothing to do with Haskell monads, so I apologize if it causes a little bit of confusion. Monadic functions always have a word name, and they take the argument to the right. So for example, we can take the absolute value of -1, or we can do till 10 to get the first 10 integers. Till is how we generate vectors, so I'll be using it over and over in the examples to come. Dyadic functions are just functions that take two arguments. Verbs are functions that appear between their arguments. So dyadic verbs are things like this that we're familiar with, addition, 1 + 2 is 3. But they don't have to have a symbol. They can also have a word name. 9 mod 3 is 0. That's just the modulo operation. It turns out in Q we also get function application as a verb, which turns out to be really handy. There's two forms of function application. There's monadic function application, represented by the @ symbol. So here we're applying the monadic function absolute value at the argument -1, giving us the result of 1. And dyadic function application is represented by dot. So here we're giving it a dyadic function, minus, and the two arguments giving us 1 - 2. Primitive functions in Q are what are called atomic, meaning that they apply to atoms. And this is really where vector languages start to get their expressive power. So for example, instead of having to map a multiplication over a list, we can just directly multiply a scalar to a vector and get exactly the result that we would expect. You can see where this gets to be powerful in, for example, this last example here. I have this deeply nested array structure. It could be a tree or hopefully has some meaning in whatever domain you're in. But I'm taking that nested structure and just multiplying that whole structure by 5. And I'm not having to write some recursive computation to descend through that thing and multiply all of the atoms. It's just done for me. You might notice in these examples that the result might not be what you would expect. For example, in this second thing, why that is because in Q, evaluation is always right to left. So in that second example, we're generating the vector till 5. Then we're adding 10 to it, and we're multiplying that by 5. This is a bit strange to get used to, but it turns out to be a huge productivity win. It means we never have to look at infix rules for code that we're not familiar with or code that we've not seen before. And we never have to look at Q's operator precedence, because there just isn't any. You always just evaluate right to left. Even though it's evaluated right to left, it's typically read left to right in a top-down sort of fashion. That tends to be a good hint when you're writing Q, because if you can't read your line left to right, you're probably trying to put your entire program into one line. So it turns out when you're working with lists, list primitives are extremely important. So we can do the usual sorts of things, we just do them in fewer characters. So we can take from the head of a list, we can take from the tail of a list, we can join two lists together with comma, and we can split a list based on some indices. So here I'm splitting the list till 9 on the indices 0, 3, and 6, giving me a lovely little 3x3 matrix. So mapping a list, this is something we do in functional programming all the time. In Q, we can do it as well. So we have our 3x3 matrix here. We want to get the number of elements in each row of this matrix. There's a function count that gives the length of a vector. And if we do count each 3x3 matrix, it counts each of the rows, giving us a vector of the lengths. But it turns out in Q, we can also map dyadic verbs. And this turns out to be hugely powerful. This is something I've had to do in just about every functional language I've used. What I typically have to do is I'll have two lists. I'll have to zip those lists together into a list of pairs. Then I'll have to map some lambda over that list of pairs that applies some dyadic verb to each, or dyadic function to each element of that pair. In Q, we can do that entire line of reasoning with a single character. That character is tick, and we call it each both. And this is the first adverb that we've seen. What an adverb is it takes a verb, a dyadic verb, and modifies that verb's behavior. So for example, we have the take verb, 3 take 0 repeats 0 3 times. If instead of having a scalar on either side of take, we can apply a list or a vector on either side of take and modify the take with this each both. And what that does is it essentially zips those two lists together and applies take to each of the pairs. We're just implementing that with one character, giving us that 3x3 matrix. So the general form of an adverb, it always just follows a verb, and it has both of that verb's arguments to the left and right. So in the example that we just saw, we have a noun argument on the left, a noun argument on the right, the verb that we're modifying here, that's take, and the adverb that's doing the modification, which is each both. So here's a few more adverbs that you're probably familiar with, fold and scan. This is some more FP 101 type stuff. Fold, you might call it reduce, we call it over. We represent it by a forward slash, and it just does a reduction of a verb over a list. So for example, if we do plus over till 5, it sums up the numbers 0, 1, 2, 3, and 4. Scan is sort of the counterpart to over. What that does is it returns the iterative values leading up to the final value of the over. So if we do plus scan till 5, it gives us all of the partial sums leading up to the final sum 10. And that 0 on the left of both of those is just the initial value. So it turns out there's only 6 of these adverbs, but they come up all the time when we're working with lists. We've already seen half of them. We've seen each both, we've seen fold, and we've seen scan. There's also each right. What that does is it pairs the argument on the left with each element in the list on the right. So here I'm using monadic function application to pair this max function with each row of this 3x3 matrix, getting the max of each row. Each left similarly pairs each thing in the list on the left with the thing on the right. So here again, I'm using monadic function application to apply both of the functions on the left to the scalar on the right. Each prior is an extremely handy adverb. What it does is it pairs each element in a list with the element immediately before it. So for example, if we do minus each prior, it gives us the difference between consecutive elements in a list, which is a really handy thing to be able to do, especially in a data analysis task, and we can implement that in just 3 characters. Whenever we apply an adverb to a verb, we get what's called a derived verb back out of that, meaning we can keep just sticking adverbs onto the end of it to keep changing its behavior. So one common composition of adverbs is to take each left and each right and stick them together into each left, each right. So here I'm applying both of the functions on the left, min and max, to all of the rows in the matrix on the right. So I have apply each left, each right, and it joins everything together and gives me the min and the max of each row in that 3x3 matrix. So that's a bit of a taste of Q. Those are all of the 6 adverbs available in Q, and we can use those to create expressive algorithms. I want to show 2 examples. One example is prime number generation. It's sort of a classic example to show when showing vector programming. The other example is run length encoding, slightly more practical. But before I dive into that, I first want to show the algorithm we're going to write for prime number generation, because it's a bit different from an imperative or a functional algorithm. It's important to understand how a vector programmer thinks. So the first thing we're going to do is forget that loops ever existed. The second thing we're going to do is create something rectangular. So here I have a modulo table. I have the numbers 1 to 100 on the x-axis and 1 to 100 on the y-axis. And each cell of this table is the x mod y. And it's shaded darker for the larger modulus. These are the positions in the table where the modulus is 0, exactly where x is divisible by y. We're interested in prime numbers, which have exactly 2 divisible numbers. They're divisible by 1 in themselves. So we're looking for columns in this structure that only intersect blue boxes along the y equals 1 line and the y equals x line, the itself line. If we find all of the columns where they only intersect these boxes along these two lines, we get these columns. And of course, we can do this for any integer, giving us the prime numbers less than that integer. Those columns correspond exactly to the primes. So if I flip over to Q here, we have the Q interpreter up. So one thing I can do is do 1 plus till 10. It gives me the numbers 1 to 10. I can store that in a variable called n to refer to it later on. I'll just keep everything in the same line here. What I can do is take the modulus of each left with each right, using n on either side, to get the modulo of every number with every other number, giving me that modulo table. I'm interested in the blue shaded positions, the positions where this table is equal to 0. So we can use equals, which again is an atomic operation, so it'll find the equality in the atoms of this structure. So that gives me a Boolean matrix back, true exactly where that modulo is 0, false otherwise. 0 is false, 1 is true. If we do a plus reduction over this matrix, it will sum each of the columns in this matrix, giving me for each column how many true values there are, how many shaded boxes. Q is a convenient language, so instead of doing that, we could just do the sum. And we're interested in prime numbers, which have exactly 2 shaded boxes. So if we find all of the positions where the sum is 2, we can ask where that's true to get their indices, and index back into our original list at those positions. And that gives us exactly the prime numbers less than 10. If I change that 10 to an x, which is how we refer to the first implicit argument to a function, wrap it in curly braces, which is how we say lambda, assign it to an identifier called p, we assign with colon, we now have a function that we can get the prime numbers less than some integer. So the other example I wanted to show is run length encoding. So if you're not familiar with it, what we want to do is take some string like this, lambda gem, and we want to encode each run of consecutive identical characters as a pair of how many times that character is being repeated and the character that's being repeated. So what we want is a function RLE that takes this string and produces that list of pairs, 3 L's followed by 3 A's followed by 4 M's. So we can start. If we use equality, we can find all of the positions where the character is equal to L. With equality, what we can do is modify it with this each prior adverb to see in this list for each character whether it's equal to the character immediately before it. That gives us a Boolean matrix. If we invert, a Boolean list. If we invert this list, we get the positions, we get for each element whether it's different than the element before it. We can ask where this is true, and that'll make a bit more sense if I split the original list based on these indices. So here we have exactly that list of runs. So for each run, there's 2 things we want to get. There's the number of times the character is being repeated and the character that's being repeated. So there's 2 functions I want to apply. Count is the function that takes a vector and gives you the length of the vector. And we can get the character that's being repeated just by sampling that first character. So now I'm in the situation where I have 2 monadic functions on the left that I want to apply to each of these runs that I have on the right. Well, we know how to do that. We use monadic function application. We're going to apply it to all of the functions on the left with all of the arguments on the right. If I do that, I get my run length encoded list. So I can do the same thing and convert the explicit value L to the implicit argument x, assign it to an identifier called RLE, and now I have my run length encoding function. So I'll flip back over to the slides here. So this is what we ended up with. We have prime number generation on the first line, run length encoding on the second line, and I've also included the expand function, which is the inverse of the run length encoding. Just takes a run length encoded list and creates the original list or string back out. This is extremely concise. It's only 111 bytes for this whole thing, which is really quite nice. Arthur Whitney is the person I mentioned who wrote this language, and he said something to the effect that only short programs have any hope of being correct. And you know he really believes that if you look at any of the programs he's written. That's quite a nice quote. I think there's a lot of value there. And it's quite a short quote in its own value. And it's kind of nice to note that our whole run length encoding program is even shorter. OK, so we've gotten a taste of Q. How can we use this for data analysis? And should we use it for data analysis? Well, Q is a very practical language. It's not sort of this academic exercise of, oh, what happens if we restrict ourselves to only ever using vectors? Q has other sorts of data structures that come in handy, like dictionaries, tables, keyed tables, this sort of thing. Tables are first class, and they're column tables, so operations on columns are very fast and efficient and helps with scaling and that sort of thing. It turns out that Q is actually the scripting language for this database called KDB+. And like every good database, it has a query language. It's a SQL-like query language called QSQL. It looks like this, so if you are familiar with SQL, this shouldn't be too surprising. Here we have some table called trades. We're taking the average price by symbol from trades where the date is greater than today minus 5 in the last 5 days. Q has a really big focus on temporal data types, so it has a lot of really nice temporal data types, temporal arithmetic built in, so things like if you want to add a minute value to a timestamp and get what you would expect back out. And temporal joins, things like as of joins, where you can say, give me the price for each symbol as of these times in history from this table. And it'll look at that table and backtrack in history, finding you the most recent price as of each time you requested. So let's jump into an example here. The example I'm going to show is information about people on Wikipedia and their monthly click information. It's going to be an end-to-end example. It's a fairly small exploration, but I'll be showing all of the code involved in this exploration because I want to give an idea of how much Q you actually have to type to do something more interesting than prime number generation or run length encoding. So I'm just using vanilla Q. I'm not using any libraries here. So the first thing that we need to do is actually get the data. So we can start any line with a backslash, and that line is interpreted as a system command, which is really nice because we can interact with the system without ever leaving our Q environment. So that means we can take advantage of wget to go off to the internet and get us these two files back. We're getting this Pantheon tab-separated value file and this page views tab-separated value file. So now that we have those files on disk, we're going to read those files into tables in Q. So this is what ETL looks like in Q. ETL is extract, transform, load. Here we have the file name of the file on disk. We're telling Q that it's a tab-separated file. And it has these column types, so things like I for integer, S for symbol, F for float, that sort of thing. And we're storing that in a variable called people, so that'll be a table in Q. And we're just doing the same thing for the page views table, so we'll have this people table and the page views table. But you might notice that in this page views table, there's 72 integer columns tagged on to the end of it. What that is 6 years of data. Each month in those 6 years is a single column. Now that's fine, but we're a column-oriented database, so we want to ask interesting column-oriented questions. So what we'd rather have is a long, skinny table rather than this short, fat table. So that leads to step 2 of every data analysis project, which is clean the data. A lot of people like to throw out the number 80% of every data analysis project is spent in data cleaning, data munging, that sort of thing. This data, it turns out, is already very clean. There's very little we have to do. All we have to do is take this long, skinny thing, the 72 integer columns, and convert it into, this short, fat thing, and convert it into a long, skinny thing. So what we're going to do is get the columns of this page views table, drop the first 11 columns, because those are the ones that aren't months. We're going to turn those into strings, and parse those strings into Q month values, the Q month data type. We're then going to create this long, skinny table. We'll call it monthly, and we'll give it these 4 columns, an ID column and a language column, which correspond to the primary keys of the people table, and the month and the number of times that person corresponding to the ID was clicked. We'll then do this relational left join on the ID and the language column. which are those primary keys, of the people table onto this long skinny monthly table. And we'll store that in a variable called clickinfo. So what that's doing is taking this people table and this monthly click table and joining those two together with a left join. So what I'm interested in is the computer scientists on Wikipedia. So I can just ask for the computer scientists. And that gives me something that's not too surprising back out. Relatively little traffic for computer scientists with a few prominent spikes in the traffic. So I was interested in those spikes, and I interrogated one of the spikes a little closer. Here I'm looking at the spike on the right. And it turns out that spike corresponds to Alan Turing in June 2006. June 2012. So I looked at a few of the other dimensions in the data to see if anything else was changing along this time frame, and it seemed everything else was fairly stable. The only thing changing was the clicks spiked. So I did some Googling, and it turned out that June 6, 2012 was Alan Turing's 100th birthday. So I thought back, oh yeah, I remember seeing something about that. In particular, I remember seeing this Google Doodle of a Turing tape celebrating Alan Turing on his 100th birthday. So I thought, okay, interesting. I wonder how many other spikes in Wikipedia monthly clicks have a corresponding Google Doodle. I wonder if there's any sort of correlation there. So I went to Google trying to find the nicest little data set of Google Doodles that I could to see what was being celebrated and when it was being celebrated. And I was disappointed to find that this was the best data set I could find. 6 pages of Wikipedia, 1 page per year, with each Google Doodle written out in natural language. So that's annoying. I thought we got past that data cleaning stage, but it turns out that that leads us to step 4 of every data analysis project, which is clean the data again. It turns out it's not that bad in Q. This is all we have to write to go off to the internet, get those 6 Wikipedia documents, pull those down into files, read each file into Q as an HTML file. So that's what the HTML files look like. They're just much larger. Parse each of those into a single table that looks like this, with the month of the Google Doodle and the person or thing that was being celebrated. And then aggregate all of those 6 individual tables into one giant Google Doodle table. So that's not bad for doing all of that. And if you squint at that, you can see how prevalent these adverbs are, each left, each right, these sorts of things. I'm not going to dive into this code and explain it, because it's pretty hairy, but we only have to write it once, and then we're done. If this process function here, that does all of the heavy lifting, was a lot more computationally intensive than it actually is, we might want to take advantage of these modern computers that we're using with multiple cores. We might want to make this a parallel process. So if we are good functional programming citizens and this process function is pure, we could just go ahead and turn this into a parallel process by taking this each function, which does the mapping of process over each year, stick a p in front of it for parallel. Boom, we're done. That's it. Now it's using all of the cores that you have available to you. So now that we have our doodle table, we have our click info table, we can do a little bit more interesting analysis. So all I'm doing here in the first line is creating a new column of the click info table, which is just a Boolean column, indicating if that person is celebrated in that month. In the next 4 lines or so, I'm asking for each doodled person, what is the difference between their doodled traffic and their next highest traffic, what their traffic would have been had they not have been doodled, to our best estimate, because we don't know what that would be for the month that they were doodled. And it turns out, on average, or their mean, it's 58 times higher. Their doodled traffic is 58 times higher than their next highest non-doodled traffic, with a median of 10 times. So that's fairly significant. That could lead to a bit more of an exploration there. And those are the 6 or 7 people with the highest difference between their doodled traffic and their next highest traffic. So it's kind of nice to see an appearance from Grace Hopper there. So in the interest of time, I'll stop the exploration there. But we went from having no data to finding an interesting result in the data from multiple data sources, doing a little bit of data cleaning, data munging, and joining there. So we'll do a quick summary here, and we'll take some questions. So why should you care? Well, we went over that Q has a very high-level expressive notation. You can write complex algorithms very quickly, really at the speed that you can dictate, at least, as I did with run-length encoding and prime number generation. I think it's important to note in this age where functional programming is really starting to have an impact and all of these languages are popping up all over the place, it's important to note that this isn't just someone's pet project, and it's not just going to be abandoned or disappear in a year or so. this is developed by a company called KX Systems. They've been doing this since 1993 at least. And the vector community has been doing this since APL, since 1965. Q is a very practical language, so we talked about things like dictionaries, tables, keyed tables, this query language QSQL, which is actually just syntactic sugar over Q functions. So it's fully integrated in the language, it's just an expression. This focus on temporals, temporal data types, temporal arithmetic, temporal joins, and tons of other practical stuff that I just don't have time to cover. It's very fast, and it's only going to get faster. If you're interested in the performance, I can only urge you to check out the benchmarks online. I don't want to make any enemies here. It's interesting, it's different, and it'll change how you think and give you a new way of looking at problems. I think that's helpful in any programming language. So that's it for me, if anybody has any questions.